All right. So today and tomorrow, we want to finish up Taylor series. Today, I want to focus mostly, as I was saying, on sort of the remaining techniques we have with Taylor series, and then we have Taylor's remainder theorem, which is technically in the section for today, but it also leads into what we're talking about tomorrow. So if we don't get to it today, we can talk about remainder theorems tomorrow. The other problem with the remainder theorems is sometimes, even though we have Taylor's remainder theorem, sometimes it's easier to use other remainder theorems. And like if we're trying to evaluate a Taylor series to a certain degree, based on the values that we are evaluating at, we often get an alternating series out of that, which then we can use the alternating series remainder theorem. So it ends up being easier. Taylor's remainder theorem ends up being a little difficult. It's just more involved than the other remainder theorem. So for now, let's start off with the binomial series. This one's probably the most important thing that we haven't talked about yet, or at least the next natural thing. We ideally want to extend our building blocks. Let me see if I have that list handy. I do not. But last week we started our list of building blocks of power series and Taylor series, and we've got a pretty good repertoire now of most of the common functions that we've seen throughout Calc 1, pre-calc, and beginnings of Calc 2. We want to include more functions though, or at least as much as we can. So we haven't gotten to arc sine or arc cosine. Arc sine we'll be able to get with the binomial series. And then we would also like to get something like tangent. So we've seen the building blocks for our trig functions, our standard trig, sine and cosine. And from sine and cosine, we can essentially develop all of the remaining trig functions with mathematical operations. So we'll have to actually figure out how to do multiplication and division in particular with Taylor series. So let's start off with our binomial expansion. So our function is just going to be 1 plus x raised to the k, where k is any real number. So if k is an integer, positive integer, we know how to expand it. We can multiply everything out. And I don't know if your instructors for either Calc 1 or somewhere in pre-calc or in high school have showed you this, but this is going to be related to Pascal's triangle. So what is Pascal's triangle? It kind of tells us the coefficients within each row. So just to start off with an example to kind of lead us into this a little bit, if we have a function f of x is equal to 1 plus x cubed, we could cube everything out. And what are you going to find? Well, our cube is over here in 3. We will find that this is our line of coefficients. And so it's going to be 1 plus 3x plus 3x squared plus x cubed. And so if Pascal's triangle gives us the formula for the coefficients, then the exponents, what you want to think of as a product of the two terms, where the degree of each term is raised, the sum of the degrees is equal to 1. So you can think of this one as 1 cubed. This one as 1 squared times x to the 1, 1 to the 1 times x squared, and then 1 to the 0 times x cubed. If we had changed this to a y, we would see the y's there. So I guess to illustrate that, if we have x plus y, our binomial theorem, when we expand that and do all the multiplication, we will have x cubed plus 3 x squared y plus 3 xy squared plus 1 y cubed. So you can see how we pick the first first variable or the first term there, and it's going to start with a cube, and then the powers of that are going to decrease by 1, whereas the second one is going to start at y to the 0 and then increase by 1 for each consecutive terms. And it gives us a nice way of just writing these down, so that way you don't have to compute it. So if we had something like, let's call it a plus x to the fourth, you really can just write it down. So our coefficients are now going to follow this fourth line. The powers of a go down as the powers of x increase. Where does it, excuse me, where does this come from? If you haven't seen how to come up with the next row in Pascal's triangle, it's fairly easy. The ends are always 1. And then how would we come up with the terms here? We just add up 1 and 4 will give us 5 here. 4 and 6 will give us 10. And so we just add up the two terms adjacent to it. So there's actually a mathematical formula for it called the binomial theorem. However, we're actually going to extend it a little bit beyond, because the binomial theorem in actuality is going to use factorials. It's going to be highly used in probability. So if any of you guys are getting into like data science and you have to take stats and probability, you'll see this quite a bit. Or if anyone has to take like discrete math or any sort of combinatorics, you will for sure see this again. The problem is for calculus, well, now we have this problem of what happens if k is a real number. This is nice when k is an integer to organize our work this way, but what's going to happen if k is, say, 1/2? Right? We've seen a lot of these functions come up where we have polynomials underneath square roots. We've got fancy integration techniques and stuff to deal with those. But as we've kind of seen from that, they're hard to work with. Square roots, especially if the expression underneath a square root gets a little more complicated. For example, if it's a degree 3 polynomial underneath a square root, we don't really know how to work with those very well in terms of our integration. Differentiation, not too bad, but integrating, we can't do something like that. And so what we can do is use our Taylor series to actually work with those expressions, work with those types of functions just with their Taylor series. So let's take a look. We've got f of x equal to 1 plus x to the k, where k is some integer, or sorry, not an integer, some real number, so potentially fraction. K could be pi. And we want to go through the process of finding a Taylor series for it. So let's go ahead and compute our derivatives. F prime of x is going to be k times 1 plus x. Nicely enough, at least with the expression underneath the parentheses, there's not too complicated, and the chain rule is just going to give us a times 1 every time. So our f prime of x is just going to pull down that factor of k. F double prime, we will have k times k minus 1. And f triple prime And so if we were to keep going, when we have n derivatives, well, what does this term look like it's going to be? If I take 3 derivatives, I have k times k minus 1 times k minus 2. So as I take n derivatives, we're going to have k times k minus 1, k minus 2, and we're going to keep multiplying. But we're going to stop at k minus 1 less than the degree, or than the number of derivatives we're taking. And then we will have a times 1 plus x to that same degree, k minus n minus, sorry, that should be a 3 there. So that one should just be k minus n would be the remaining degree on that. And so someone has mentioned in the chat, factorial. Good. Good observation. So we have this factorial process going on. It's a little weird though, because what if k is not an integer? So we really don't have a factorial process defined for values that aren't integer values. So let's take a look and then take a look at this conundrum of factorials. Let's evaluate first real quick. And then we'll take a look at how we can write that and what is going on with this factorial-like process. So when we evaluate our fn of 0, we're still going to get this k times k minus 1, k minus 2, all the way up to k minus n minus 1. And then when we plug in a 0 for x, of course, we're just going to be left with a 1 to the k minus n. So that's just going to be a 1, and we're going to left with this product of descending values. I'll go ahead and multiply that minus sign through as well. So if k is a natural number, then we can express this as well, we've got a k factorial in the numerator. However, we don't go all the way down to 1. We stop at n minus 1, which means we would need to divide by n factorial. Sorry, I wrote that wrong. I'm trying to think. I was like, yeah, that doesn't work right. The problem with the book and the notation is that usually our n's are on top, and our k's, the role of k and n in this process is flipped from the typical derivation of the binomial formula. So it's going to be k minus n factorial, right? So we'll have k times k minus 1 times k minus 2, k minus 3, all the way up to k minus n minus 1. The next term is then going to be k minus n minus 1. And so all of those extra terms that we don't see in this product, we're going to have here. And so the power series if k is an integer, Taylor series is going to be, so this is our formula for the nth derivative evaluated at 0. We will then have to divide by 1 over n, or multiply by 1 over n factorial by the formula for our Taylor series. And we will have an x to the n. So this guy is known as a choice function. So this is k choose n. It's how we notated it. It's kind of like a vector. It's kind of just a parentheses with 2 numbers on top, and we read it as k choose n. And this works nicely when k is a natural number, but the problem is if k is not a natural number, then k factorial doesn't make sense. In particular, if we try 1/2 factorial, well, that's going to be 1/2, but then as soon as I subtract 1, it's going to be times -1/2. And then if I subtract 1 times -3/2, and then we would theoretically just keep going and going and going. There'd be no natural stopping point. And so we'd have a product of terms. It would be alternating, but what's going to happen to the terms? We've got 3/2, next one's 5/2, next one's 7/2. The product is essentially going to be infinite with those. So dealing with a fractional factorial, it would be, by definition, infinite every single time. So it's not a great way to define it this way. Though it's not entirely wrong, at least the process, when we're talking about what's going on in terms of sums and series. So in general, we essentially want to just keep our formula for the nth derivative as this. This process holds. This was our formula for computing n derivatives. We didn't introduce any sort of fancy factorial notation or anything yet here. And it was just under the assumption still that k was a real number. And so for any real number, this will be the nth derivative. So that is kind of what we have to write it out as. It's not incredibly nice, but hopefully at least the notation, it's easy enough to understand. So we are going to have a k times k minus 1, k minus 2, all the way down to k minus n plus 1. That n factorial, remember, comes from the derivatives, comes from our formula for Taylor series. So that n being an integer, n factorial does make sense. And then times x to the n. And so let's just rewrite the function to reiterate. Our 1 plus x to the k was what we were looking at for this Taylor series. Okay. So let's do a couple of examples. Example, let's find our Taylor series for 1 over square root of 1 minus x. B, find our Taylor series for arcsine. So for A, we've got our f of x. Now we could go through the Taylor series process again, our general process of computing derivatives and all that. But once we've computed these derivatives and these Taylor formulas for these general classes of functions, it gets easier to derive more, because then we don't have to go through that whole process. We can just use our algebraic and calculus skills to work on known power series in Taylor series. So here's our function, 1 minus x all raised to the 1/2, negative 1/2. And so by our formula, what are we going to have? We should have that f of x is equal to the sum k times k minus 1, k minus n plus 1, all over n factorial. And then our x, we had a minus x raised to the n. And our k in this case is going to start at negative 1/2. So it might be easiest to start and just write this out with our sequence of terms. So the first term, when n is equal to 0, our coefficient is just going to be k. Let me check that. So when there should be 0, 1, up to n. Yeah. No, hang on. Our binomial theorem, sorry, I'm confusing our terms here. We want to take a look at when k is equal to 0. So of course the problem with writing it this way is we do have to understand how many derivatives we're taking. So of course if we take n derivatives, let's look back on this. So this is our formula for n derivatives. When we had 0 derivatives, where is it? Here. So our 0th derivative, when of course x is 0, our coefficient is just 1. So our 0th order term should just be 1. And then the next one's going to be k. So our n equals 1 term, we should have a minus 1/2 x to the 1. It's going to alternate by that minus 1 there. So we will have then a plus. Now I go minus 1/2 minus 1. So that'll give us a negative 3/2. And then times that negative will give us a positive. And then the next term will be, oh, sorry, and I forgot. So it's going to be a 1/2 times that. 1/2 times our 3/2. Then it will be a plus. So let's keep track of the minus signs and see what's going on here. Our coefficients are going to be minus 1/2, minus 3/2, minus 5/2. So I actually think I missed a minus sign here. So it's a minus 1/2, but when n is equal to 1, we will have a minus sign here. So not only are we having these minus signs come in from our coefficients, our minus 1/2, minus 3/2, but then we also have this alternating piece from that minus x we got to work with. So we will have a minus 1 cubed, x cubed. And so the minus signs will all end up canceling actually. And what are we left with? So we're left with 1 times 1/2 x to the 1, or sorry, plus 3 over 2 to the n, x squared, or sorry, 2 squared. I'm getting ahead of myself for that formula. Times 1 times 3 times 5 in the numerator over 2 to the n in the denominator. X cubed in the numerator. What will the next term be? 1 times 3 times 5 times 7.
Isn't it 2 cubed, not 2 to the n?
Yes, thank you. I keep writing that n. 2 cubed, and then 2 to the 4th, x to the 4th. So, what is our formula for this? Unfortunately, writing these guys out, we can't really write out nicely in terms of a factorial. So this formula might be the best way to write it. Or sometimes with these ones, we just write out the first few terms and list the pattern, especially because you guys don't know product notation. If we wanted to try to write it, it's going to be, let's see, so starting from n is equal to 0 up to infinity. It's going to be something like that, but we're going to need to write this as a product. So 2n plus 1, when n is equal to 1, we should have 1 times, let's check this. So when n is equal to 2, we will get 5. Problem is when n starts at 0, we don't want to put a minus sign here. So let's trying to come up with a nice or closed form expression for something like this. We just have to be careful with how our index starts. So if we're starting at n is equal to 0, so we certainly have a 2 to the n in our denominators. And then the numerator is going to start from 2n minus 1. And then times 2n minus 3 times all the way down to 1 times x to the n. It's about as close as we can get. The problem is when n is equal to 0, that doesn't quite work. So maybe we'll start this at n is equal to 1, and then we might have to add a 1 plus on the outside, since this 1 isn't entirely described by that sequence. So this is our formula for this square root, or square root of 1 over square root of 1 minus x. And now we want to get a series for arcsine based off of this. So we should note that arcsine of x is the antiderivative of 1 over square root of 1 minus x squared. Dx. And since we now have a series for 1 over 1 minus x, we can come up with the series for 1 over square root of 1 minus x squared is going to be the series we just found, except now I'm going to stick an x squared in for all of those. So it's going to be a 1 plus, we're going to have 1/2 x squared. We're going to have plus, let's go ahead and write it as 3 over 2 squared. X squared squared, so x to the 4th, plus 5 times 3 times 1 over 2 cubed, x to the 6th. And then so to integrate that, so our integral of all of these and when we integrate term by term, see if I can keep this on the screen. What are we left with? So we will have our constant of integration plus x plus, and now we've got to divide. So here we will have a 1 over 2 times 2, 2 times 3, excuse me, x cubed plus 3 over 2 squared times 4, x to the 4th, plus 5 times 3 times 1. We had our 2 cubed. Oops, sorry, x to the 5th. I'm forgetting my even odd terms. 2 cubed times x times 7 times x to the 7. And then that will keep going. So the next term, 7 times 3, 7 times 5 times 3 times 1 in the numerator, 2 to the 4th, and then times a 9 in the denominator times x to the 9th. To get rid of our constant, we know that arc sine of 0 is 0. So if I plug in zeros for all of the x's, we'll get that c is equal to 0, meaning that our series for arc sine is x plus 1 over 2 times 3 x cubed plus 3 over 2 squared times 5 x to the 5th plus 5 times 3 times 1 2 cubed times 7 over, or times x to the 7th. And let's put one more term where we'll have our 7 times 5 times 3 over 2 to the 4th times 9, and that will be our x to the 9. So how do we come up with a nice or closed form expression of this guy? We've got to be careful with our indices. Let's consider this. So x equals 1, or excuse me, n equals 1. Our n equals 2 term is going to be this guy. This will be n equals 3, n equals 4, n equals 5. So we are going to have an x to the 2n minus 1. Our coefficients wait a second. Did I miss a factorial somewhere? I did I not? Uh-oh. All right, we got to go back. It's going to be even more complicated. We forgot the factorial terms. So when I was multiplying these guys out, I was multiplying out the 1/2s and all these decreasing powers of 1/2. We forgot this guy. So it's going to make it even more messier. But that one's not going to be too hard to throw in. So that's going to be 0 factorial, 1 factorial. We should have an extra factor of 2 in the denominator here. And then here we will have a 1 over 3 factorial with our x cubed term. So all in all, we should have a 3 factorial, a 2 factorial, a 3 factorial, a 4 factorial here. And then in our closed form expression, we just forgot the n factorial there. Putting that back in here, our 0 factorial or 1 factorial, we should have our factor of 2 here, our 3 factorial here. 4 will be with the next one. Let's make sure we're putting those in. So this was our 0, our 1. We should have a 2 factorial, a 3 factorial here, and then a 4 factorial with that next one. So 0, 1, 2, 3, and 4 factorial. So let's write all that out. Going to be a little messy. So let's collect our powers of 2 first. That might be easiest to write out. So we should have a 2 to the n minus 1. So if n starts at 1, we'll have that 2 to the 0. When n is 2, or n is 1, we'll have
just 2 to the n, I think, isn't
it? So I think we're going to want to start at n equals 1.
Oh, okay.
So this was our n equals 1 term. So when n equals 1, no powers of 2. N equals 2, we'll have 1 power of 2. N equals 3, 2 powers of 2. We're going to need our 0, 1, and then 2 factorial. So the n factorial is going to stay. And then the last term we're going to have to deal with is these odd terms that are coming out. So 1, 3, 5,
2n
7,
plus 1.
9. So we get a 2n plus 1. Good. 2n minus 1, I believe, yeah. Because we're starting at n equals 1.
Sorry, I'm still thinking n equals 0.
Yep. And then numerators, I think we just have to write out the product. Unfortunately, there's not a nice way to do that. And this was our n equals 5, starts at 7. So n equals 4 goes to 5. So it looks like we're going to have a 2n minus 3 will be the highest term. And that might be a problem if we start at n equals 1 because it's not going to model this coefficient here. So again, we actually might have to start at n equals 2 and then pull out this coefficient of x. Because if n is equal to 5, we should get that. Yeah. This is not a nice closed form expression. The way the book deals with a lot of these sequences, if you can get to this part, that's basically good enough, especially for these more complicated ones, because then that product's going to go down. So the way it's written, we would actually have to start with n equals 2. Since n equals 1, we would have a negative coefficient here. Wouldn't make sense, and we actually have to bring that x outside. Any questions on this guy? So our basic idea is to use this binomial expansion and now this binomial formula for a Taylor series. Now we've got a new class of functions we can work with, and a whole host of extra problems and extra Taylor series that we can come up with. Lewis, what are you guys doing in recitation today?
It looks like various applications of Taylor series and evaluating things by recognizing them as Taylor series and the like.
Okay, that's good, because that's kind of related to this, and just, manipulating different functions. Other things we kind of need to get into, I don't know if you guys want to go through this, but products and quotients. So trying to come up with functions now like Taylor series for e to the x sine of x, or even if we wanted to come up with a Taylor series for tangent of x, we now need to divide Taylor series. If you guys have time, and if you guys want to touch base on those, that would be great. I think tomorrow I was telling the class we'll get into the remainder theorem stuff. So I'm not sure if you guys were going to talk about that, but we can hold off on that. And then, the other topic. Limits are actually pretty easy. So for example, if we want to compute the limit as x goes to 0, let's see, what's the example I had? 1 minus cosine of x over 1 plus x minus e to the x. So we have standard L'Hopital's rule practices we can do. But now, if we know Taylor series, we can avoid using L'Hopital's rule, especially if the derivatives are going to look rather complicated, and just evaluate it with Taylor series fairly easily. So if you guys want to go over any of those topics in recitation, feel free. But of course, practicing coming up with Taylor series representations using manipulations, also a good thing to go over and practice more with. Any questions on anything? All right, so I'll go ahead and turn it over to Lewis, and then I'll see you guys tomorrow.